Hello, I'm Kemal Oksuz, and in the last part of this tutorial, I will discuss optimization of performance measures. In this part of the tutorial, we will focus on how the performance measures can be optimized as loss functions. The main challenge in this optimization is that such loss functions derived from performance measures are non-differentiable. And to overcome this challenge, we will revisit identity update as a general framework to obtain loss functions from average precision and LRP error. The first question to ask in this part of the tutorial is whether optimizing a loss function always implies optimizing the performance measure of a task. Even comparing the widely used cross entropy loss function with accuracy presents that it does not. Let's assume that we have three different classes and three examples, each of which belongs to a different class. And during training, we obtain two different sets of predictions of these three examples, prediction 1 and prediction 2. Comparing prediction 1 and prediction 2 in terms of cross entropy and accuracy, we can observe that while prediction 2 has a lower loss value, prediction 1 has a higher accuracy. This presents a counterexample on a case where optimized loss function may not optimize the performance measure. Then we can ask a follow-up question. Why don't we use performance measures as loss functions? This is mainly because computing performance measures in general involves non-differentiable counting operation. I use the term non-differentiable to refer to an operation when its derivatives with respect to its inputs are either 0 or infinity. Let me present the problem on a toy example. Stochastic gradient descent update rule, which dominates the optimization of deep learning models, updates a learnable parameter of the model, Wi, by using the derivative of the loss function with respect to Wi. This derivative can be decomposed into two multiplicative parts. The first part, the derivative of the model output with respect to the weight, comprises of sequential differentiable neural network layers and can be computed using backpropagation. On the other hand, the second part, the derivative of the loss function with respect to a network output, Sj, depends on the loss function. Comparing cross entropy and the loss form of accuracy, we can see that while cross entropy loss has a smooth surface providing useful derivatives for stochastic gradient descent throughout its domain, accuracy loss has a step-like structure with only derivatives of either 0 or infinity. Hence, it cannot be directly incorporated into stochastic gradient descent. We will refer to such functions as ranking-based loss functions, which can be defined as the loss functions involving a Boolean comparison, psi, between two different model outputs, Si and Sj. The comparison function can be represented by Heaviside step function h, considering the differences of these model outputs, which is non-differentiable. As an example, on binary classification task with positive and negative classes, we can define a loss function as the average number of negative examples ranked over positive examples, namely the number of false positives, which can be represented by the expression in the screen. Then, given 5 examples from positive and negative classes with the shown confidence scores, this loss function is minimized when all positives are ranked above all negatives. And it is computed by thresholding the detections on each positive and counting the number of negatives ranked above the corresponding positive. Thresholding from the first positive, we have one negative ranked above that positive, and for the second positive, there are 3 negatives. Accordingly, the overall average loss value for this toy example is 2. In this part of the tutorial, I will first introduce identity update as a general framework to optimize these ranking-based loss functions. And then I will discuss how average precision and LRP error can be converted into loss functions by using identity update framework. More particularly, I will introduce average precision loss for classification tasks, and then for visual detection tasks, I will introduce average LRP and rank and sort losses. both of which rely on LRP error introduced in the first and the second part of this tutorial. Let me begin with identity update. Let's briefly revisit perceptron learning, since identity update relies on error-driven update from perceptron learning. Perceptron aims to learn a weight vector W that classifies the input X between two classes. As an example, assume that there are two examples from negative class and one example from positive class, and we want to split positive and negative classes by a hyperplane represented by its normal, the green arrow in the figure. The general convention is to initialize the normal vector randomly and then, having observed the data, update it according to improve the classification performance. One of the most straightforward approaches can be to set the normal vector to the example itself when the observed data belongs to the positive class and the model makes a mistake predicting it as a negative. Else, if the label of the observed data is negative and the prediction is positive, it is set to the opposite direction of the example. However, with such an update rule, the normal vector will oscillate and not converge. Instead of these large changes, error-driven update aims to update the weights slowly when the model makes a mistake. For example, having observed the positive example in this setting, the normal vector is shifted towards this example slowly. The corresponding error-driven update can be simplified into a single equation such that W is the model parameters, X is the input data, T is the prediction of the model, and T star is the target label of the data. Inspired by the work of Chen and his colleagues, identity update uses error-driven update from perceptron learning, and it is proposed as a general framework to optimize ranking-based loss functions. It assumes a ranking-based loss function to follow the form in the left side of the screen, in which the loss is the normalized sum of the differences between the current error computed on example I, that is Li in the screen, and its target value, that is L star I in the definition of the loss. For example, for our toy example, Li is the number of negatives ranked over ith positive. The target term is 0, since the number of negatives is 0 when we rank all the positives above negatives, and the normalization constant is the number of positives. In order to generalize the idea, we need to answer two questions. First, how can we compute the ranking-based loss function given model outputs? And second, how can we find an update for model outputs, namely the backpropagation step? To do so, identity update exploits a three-step algorithm. First, the differences between each pair to obtain pairwise relations are computed. Then, given these difference transforms, primary terms that are the error originating from each pair are computed such that the normalized sum of these primary terms yields the loss value. To obtain these primary terms, the error computed on ith example is distributed over other examples by a probability mass function. Note that examples other than I contribute to Li. For example, in our toy example loss function, the scores of the negative examples directly affect the error computed on ith positive example. Hence, to obtain pairwise error, the error needs to be shared with its contributors. It has been also proven that this formulation yields to the desired loss value. As for the backward pass, the first and the last steps are differentiable, and it has been shown that the error value can be directly adopted as the update for the second step, and the resulting total gradient magnitudes are equal for positive and negative classes. Note that one only needs to define the loss function and determine a probability mass function, which make the framework general and simple. Now I will continue with average precision loss, AP loss in short. In this part, I will revisit the classification task, derive average precision loss without and with identity update, and finally I will provide an overview of the implementation of AP loss. Average precision loss is proposed as a ranking-based classification loss, and it is used for supervising the classifier of visual detectors. Image classification aims to infer the class label of the input image. To do so, the models output a logit for each class, which is then converted into a probability value. The first alternative to convert the logits to probabilities is to use a softmax function and obtain a probability distribution over classes. And the second common alternative is using class-wise sigmoid classifiers. Throughout this part of the tutorial, I will refer to the ground truth class logit and output as positive example, and output to be maximized, and the remaining non-ground truth classes will be negative examples. Accordingly, from this image, the zebra output corresponds to the positive example, while all others belong to the negative class. Besides, if an image does not contain any of the ground truth classes, then all the logits will be regarded as negative examples. With a similar intuition with our example number of false positive loss function that we discussed earlier, average precision loss is defined as the average of the precision errors on positive examples. Given class labels and network outputs, the aim of the average precision loss is to suppress the output of the negatives and promote the output of the positives, such that all the positives are ranked above negatives where the optimal condition is achieved. Note that the optimal condition is different than this conventional score-based classification losses, such as cross entropy and focal loss, since these score-based loss functions reach to the optimal state when the probabilities of all positives saturate to 1 and the probabilities of all negatives saturate to 0. In order to demonstrate the generalization and simplicity of identity update, I will first present how AP loss is derived by Chen and his colleagues in their pioneer paper. Given model outputs, first the difference transforms are obtained, and then primary terms for AP loss are derived by algebraic manipulations such that the normalized sum of the primary terms yields the loss value. Note that the primary term includes Heaviside step function, and Hxij corresponds to the pairwise relation between the example I and j. If the score of example j is larger than the score of example I, then Hxij is 1, otherwise it will be 0. A hyperparameter delta is introduced to smooth the Heaviside step function, while putting a margin between the samples to be ranked in order to ensure generalization. Other ranking-based terms can also be defined based on those pairwise relations. For example, to find rank I, in the denominator of the primary term, one needs to sum the pairwise relations for the example I with all other examples. Finally, to cover all the pairs in the computation, an additional variable alpha ij is introduced such that alpha ij is 1 only if I is a positive example and j is a negative one. As aforementioned, in the backward pass of this computation sequence, the first and the third terms are differentiable while the second one is not. Hence, the authors replace that non-differentiable part by error-driven update, that is the difference between target and current values. And in the target ranking, AP loss aims to rank all positives above all negatives, implying 0 error, namely 0 primary term. Note that beyond generalizing this optimization strategy, identity update offers simplicity. since the primary terms are not derived, but they are defined based on the definition of the loss function, and no additional variable such as alpha is required. Let me introduce how we derive the update with identity update, which includes a three-step framework that are defining the loss function, computing the loss function, and optimizing the loss function. In the first step, we define the loss function from identity update perspective. Namely, we need to define the error value on a single example, that is Li, and its corresponding target, that is L star I. For AP loss, the error is simply the precision error presented at the left part of the screen, and the target on a single positive example is to rank positives above negatives, which implies perfect precision that makes the precision error 0. Then, to compute AP loss following identity update, we obtain the primary terms as the products of the defined errors on a positive example and probability mass function. The probability mass function distributes the error uniformly over other examples, causing the error. More precisely, for positive-negative pairs, the ranking probability mass function distributes the error computed on ith positive uniformly over negatives with logits larger than the ith positive example. This is because if there is ranking error on a positive example, this is due to the negatives with larger scores. This ranking probability mass function expression corresponds to this operation. In such a way, the primary terms as the pairwise errors can be obtained and the loss value can be computed. Note that obtaining primary term using its definition is significantly simpler compared to deriving it. Finally, for optimization, we replace the non-differentiable part by primary terms and simplify the expressions for negative and positive examples. In such a way, we obtain the update expression of the loss function with respect to the logits, concluding the derivation of AP loss, computation, and optimization using identity update. In the left side of the screen, the implementation of AP loss is presented. Different from the conventional score-based loss functions with linear time and space complexity, average precision loss requires the relations between all pairs, and as a result, it has quadratic time and space complexity. This especially makes the training of object detectors challenging, since object detectors can have hundreds of thousands of examples, making it infeasible to use such loss functions directly, especially due to the space limitations of GPUs. To alleviate that, two training tricks are employed. First, the negative examples that do not contribute to the loss, namely the ones that are already classified properly with the desired margin, are discarded from the computation in the beginning of the implementation. And second, instead of computing the update at once, the updates are computed on each positive example sequentially implemented by a loop. Now let's consider the computations in a loop given the example input at the top right of the screen. Note that the loop runs over the positive examples and assumes that the computation is on the green positive example. In the loop, first the precision error LAP is computed, which is 0.6 on the green example, since there are 6 negatives and 10 total examples with larger scores than this example. Note that this error directly corresponds to the normalized update for the positive example. As for the negative examples, in order to implement the probability mass function, the ranking error is divided by the number of negatives, and the resulting error is cumulatively summed within the loop. Hence, the higher a negative has a confidence score, the more update it will receive from other positives to reduce its score. In this example, the update of all black negatives increases by 0.1. Finally, following the update expression, all updates are normalized by the number of positives. The experiments suggest that AP loss performs better than focal loss in object detection tasks on COCO and Pascal datasets. Note that similar to focal loss, AP loss is robust to class imbalance and hence does not require any sampling heuristics to alleviate positive-negative imbalance inherent to object detection. Next, I will continue with average localization-recall-precision loss, average LRP loss in short. Average LRP loss is designed specifically for object detection in which the aim is to classify each object in an image also by localizing them by bounding boxes. This slide presents an overview of the common object detection pipeline along with some key concepts. In order to reach the desired output, the image is fed to a backbone network, which can be a combination of ResNet and feature pyramid network, and the features from the entire image are obtained. Then, in the pipeline, there exists a subnetwork for each task. Given the extracted features, the classification network aims to classify the objects, and the localization network regresses the bounding boxes of the objects. In order to capture all objects in different locations, scales, and aspect ratios, the image is divided into sub-regions which are called object hypotheses or anchors in general. If an anchor overlaps with a ground truth box significantly, then we expect the classification network to classify it with the label of the object and the localization network to map the anchor onto the bounding box of the object. Otherwise, if the anchor does not correspond to any of the objects, then the classifier is to classify it as background and the localization output is irrelevant in this case. Since there are many anchors, the same ground truth can be targeted by several anchors causing duplicates. Generally, non-maximum suppression, or NMS in short, is employed to remove the duplicates and to yield the final detection output. In some detection pipelines, there can be more than one pair of classification and localization networks, which can be regarded as multi-stage detectors. Finally, to measure the proximity of two bounding boxes, green and blue boxes in the image, intersection over union is adopted as a common overlap measure. As the name suggests, given two boxes, we measure their union and intersection and then estimate the ratio. If the green box gets closer to the blue box, then their intersection will increase and union will decrease, implying a better overlap. IOU is used, for example, while matching the anchors with ground truth boxes. An anchor is positive if it has a large IOU with a ground truth box, else it's a negative anchor and needs to be classified as background. This pipeline is trained by a multitask loss function, in which there exists an individual loss function to train each subnetwork, which are then combined by a scalar lambda. However, this formulation has drawbacks. First, mainly due to the imbalance problems, the methods tend to introduce many hyperparameters. For example, when we simply use gross entropy loss, due to the significant imbalance between positive and negative anchors, the classification loss drops directly to zero in the beginning of training. This is due to overfitting for background classes since the network classifies all anchors as background. Note that such a detector effectively does not learn anything. As a common solution, focal loss introduces two hyperparameters, and in general, the number of hyperparameters can easily reach 10, which makes the loss functions of the object detectors hard to be tuned. Besides, this common loss formulation ignores correlating classification and localization networks, which influences the performance. Here I will illustrate the effect of correlation on non-maximum suppression. Let's assume that there are three overlapping boxes, blue, white, and red, which are shown in the top right image on the screen. And non-maximum suppression will survive one of them. if the confidence scores and IOUs of the predictions positively correlate, then non-maximum suppression will survive the one with the best localization as shown in the NMS output at bottom left image. On the other hand, if the correlation decreases, then NMS will end up with the one with the worst localization quality. Note that this loss formulation combines losses independently and ignores this correlation. Finally, as illustrated before, while the pipelines of one-stage and multi-stage methods are similar, the methods employ different techniques to alleviate class imbalance. Commonly, one-stage methods are trained without sampling but with focal loss, whereas multi-stage methods use sampling and cross-entropy. However, a robust solution to class imbalance should be able to train all approaches providing at least the same performance. These three drawbacks can be addressed directly by optimizing performance measures, namely by bridging the gap between training and evaluation. Average LRP loss is an attempt to close this gap. Different from average precision loss, which optimizes precision error, average LRP loss optimizes localization-recall-precision error, which is a performance metric for object detection combining classification and localization qualities as discussed in the first and the second parts of this tutorial. There are two assumptions while converting LRP error into a loss form. First, assuming that the anchors are dense enough to cover all objects, the number of false negatives is set to 0. And secondly, true positives and false positives are replaced by positive and negative anchors respectively to supervise the training. With these assumptions, averaging the loss form of LRP errors over positive examples, the conventional loss formulation can be replaced by average LRP loss. As a result, both classification and localization outputs are now unified in a ranking-based manner. Average LRP loss is differentiable with respect to the localization branch outputs, since the localization error is based on intersection over union, which is a differentiable function, and the classification branch outputs are constants with respect to the localization branch. Unlike the conventional losses, if a positive example has a relatively larger score, and hence it is ranked higher, first, it will have a smaller rank I, normalizing its error, and second, it will be included in the loss multiple times thanks to its positive pairwise relation H with other positives. With these two changes, the localization branch assigns larger weights on the positive examples with larger confidence scores. The same three-step framework from identity update comprising defining, computing, and optimizing the loss function can be used again. Note that this part corresponds to the current average LRP error, and the target average LRP error is defined by considering the localization quality of an example. To compute average LRP loss, following identity update, the primary terms need to be obtained using the same probability mass function from average precision loss. The resulting expression is the same, except the current and target average LRP errors replace those of average precision loss. Finally, simplifying the expression yields the updates for positives and negatives. Since LRP error assigns a localization error only if an example is a true positive, the localization branch is hardly trained, especially in the beginning of the training. To show that, average LRP loss can be split into classification and localization parts. The figure in the screen presents their trends during training. Note that in the beginning of the training, the classification part dominates the bounded range of average LRP loss, which is between 0 and 1. Also, the rate between classification and localization parts varies throughout the training. Moreover, the sum of the gradients in the classification branch approximates the loss value. Using these observations, average LRP loss employs a dynamic and hyperparameter-free self-balancing mechanism. Instead of a scalar weight, the gradients with respect to the localization output is multiplied by the ratio between average LRP loss and its localization component averaged over the last epoch. As a result, the localization branch also has similar total gradient magnitudes and the imbalance between the tasks is alleviated. Compared to average precision loss, using only a rank-based localization with a naive average LRP loss yields 1.4 average precision improvement. With self-balance, the improvement is more than 3 points. Average LRP loss has similar average precision 50 values but improves average precision 90 significantly. And the correlation between classification and localization also improves. In order to increase the mod performance and decrease training time, using generalized intersection over union and adaptive training sample selection contribute around 5 points improvement over AP loss. Comparing self-balancing mechanism with constant weighting shows that self-balance without any additional hyperparameter yields similar performance with constant weighting, which ends up with different scalars for IOU and GIOU. To empirically validate the theorem that identity update guarantees balanced training, the total gradient magnitudes of average LRP loss is compared with focal loss and cross-entropy loss. On the left, the rate of the total gradient magnitudes of positives and negatives for these loss functions is shown, and on the right, you can see the loss values during training. While average LRP loss exhibits perfect balance between the gradients throughout the training, the derivatives of focal loss have large fluctuations which biases training towards positives or negatives alternately across iterations. As expected, imbalance impacts cross-entropy more, as it quickly drops overfitting in favor of negatives, since it is dominated by the error and the gradients of this large number of negatives. In the last part of the talk, I will present rank and sort loss, RS loss in short. Different from average LRP loss, RS loss is also shown to be used on instance segmentation, which requires the objects to be localized in pixel level by masks and classified properly. Previously proposed ranking-based loss functions, average precision loss and average LRP loss, offer two important advantages. They reduce the number of hyperparameters by directly optimizing performance measures, and they are robust to class imbalance due to their ranking-based error definition. On the other hand, they need longer training with more augmentation, and they do not consider correlation by explicitly modeling positive-to-positive interactions in the classifier, which have been found useful in the literature. For example, while average LRP loss yields better results than the cross-entropy and GIOU loss combination once it is trained longer, it performs on par using the 12 epoch training setting. Also, average LRP loss performs significantly worse after the first training epoch. These are because the epoch-based self-balancing mechanism of average LRP loss tends to converge better when the model is trained for longer epochs. Secondly, the classification target of average LRP loss is not designed properly to promote correlation. One common method to promote the correlation between the classification and localization during training is to employ an auxiliary head, which aims to regress the localization qualities of positive examples. Then, during test time, the outputs of the classifier and auxiliary network are combined in order to have a joint score. The auxiliary network is supervised by an additional loss component, which is in general cross-entropy loss, since the cross-entropy loss can be employed when the target values are between 0 and 1, as in the case of IOU. On the other hand, In this setting, while the auxiliary head is only trained by positive examples, during test time the labels of the examples are not available, hence all the examples are propagated to this head, causing inconsistency between training and testing. Besides, an additional head implies more space and inference time as well. Lee and his colleagues removed this head and directly trained the classification network to regress the continuous IOU values of the examples. Training the classifier in such a way was challenging since while focal loss is robust to imbalance, it is not designed to handle the continuous labels. The authors replaced the coefficient of focal loss by the absolute distance between the ground truth label and the prediction to overcome this challenge and coined their approach as quality focal loss. RS loss has a similar motivation with quality focal loss, but differently, RS loss aims to leverage the benefits of ranking-based loss functions. Different from existing ranking-based loss functions, which do not consider positive-to-positive interactions according to train the classifier, RS loss aims not only to rank positives above negatives, but also to sort positives among themselves with respect to their continuous IOU values. This slide presents the relation between RS loss and LRP error. Rewriting the current average LRP error using the components of LRP error presents that the error is based on false positive and localization components of LRP. Since these two components are already optimized by the first two terms, their multiplication can simply be ignored. Note that the ignored term ensures the range of the error to be squeezed into 0 and 1, thereby requiring an epoch-based self-balance mechanism for the instability of an iteration-based self-balance mechanism. The resulting expression corresponds to the current rank and sort error, such that the first part measures the ranking error between positives and negatives, and the second part evaluates how well the positives are sorted with respect to their intersection over unions. Given logits and their continuous labels between 0 and 1, such as IOU, RS loss is defined as the average of the differences between current and target RS errors over positives following the identity update. And this part corresponds to the current RS loss. Given a batch of positive and negative examples, note that the current RS error on ith positive example considers all examples with larger logits, and it is the sum of the current ranking and sorting errors. While the current ranking error is simply the precision error, the current sorting error penalizes the positives with larger logits by the average of their inverted labels. Our target on each positive is to rank all positives above negatives, and at the same time sort positives with respect to their localization qualities. The RS error in that target ranking yields the target error. As a result, the target ranking error is always 0, but target sorting error can be non-zero. As identity update suggests, the primary terms for ranking and sorting are the products of the defined losses on a positive example and the probability mass function. The probability mass functions distribute the error uniformly over other examples, causing the error. More precisely, for positive-negative pairs, the same probability mass function for AP and average LRP losses are adopted. But differently, for positive-positive pairs, the sorting probability mass function distributes error uniformly on positives with larger logits but smaller IOUs. Considering that if there is a sorting error on a positive example, then this is caused by another positive example with larger score but smaller IOU. Similar to AP and average LRP losses, simplifying the expressions for negative and positive examples, one can obtain the updates of the loss function with respect to the logits. Note that, unlike negatives, the update for positives includes two terms in opposite directions. in order to sort the ith positive accordingly. While the first term aims to promote the example, the second term aims to demote it based on its interactions with all positives. This slide presents how rank and sort loss is used to supervise a generic visual detector. The upper part of the figure presents how kth stage of a generic detector is trained. There can be sampling heuristics to address class imbalance, followed by classification, box regression, mask prediction heads, and an optional auxiliary head. All these heads have their own loss functions, and then the loss functions of each subtask from each stage are combined by a scalar lambda as shown in the bottom of the slide. Once arrest loss is employed, due to the prioritization of positives by the classifier during training, detectors do not need an auxiliary head, and due to its ranking-based nature, arrest loss can handle imbalanced data without any sampling heuristics. Using GIO loss to train box regression head and dice loss to train mask prediction head ensure similar ranges of all losses. Then, similar to average LRP loss, task balancing coefficients are not tuned, but differently, they are set to the ratio between arrest loss and the corresponding localization loss every iteration. Finally, to consider classification output by the localization heads, GIOU and dice losses of the examples are multiplied by their confidence scores. To summarize the advantages of using arrest loss, first, it simplifies the training since no auxiliary head or sampling heuristics are employed, and it has been shown on 7 different detection and segmentation methods on 2 different datasets that one only needs to tune the learning rate. Second, it enforces correlation in both branches, thereby promoting better performance. And finally, it is applicable to a wide range of detection and segmentation methods. In terms of its contribution to the performance, using arrest loss with standard faster RCNN as a multi-stage object detector improves the performance by around 3 AP and 2 optimal LRP points on COCO dataset, outperforming existing RCNN variants. Arrest loss does not have any sampler, auxiliary head, and has the least number of hyperparameters. By using Carafe FPN instead of the standard FPN, the performance improves nearly to 41 AP. Arrest loss can also be used on one-stage object detectors, ATSS and PAA, which essentially differ in positive-negative assignment. Comparing arrest loss with focal loss, AP loss, quality focal loss, and average LRP loss with or without auxiliary heads shows that arrest loss outperforms its ranking-based counterparts and performs similar to quality focal loss with less number of hyperparameters. As an example for multi-stage instance segmentation, training the mask RCNN with arrest loss on the long-tailed Elvis dataset improves baseline by around 3.5 mask and box APs, especially the improvement for rare classes is notable, which is by around 7 AP. As a one-stage instance segmentation method, YOLACT has several training heuristics and carefully tuned loss weights. Removing each of these training heuristics has a significant impact on the performance of YOLACT. However, without these heuristics or carefully tuned weights, YOLACT improves the performance. To analyze its robustness to imbalance, faster RCNN is trained with and without random samplers on both stages using COCO dataset, and mask RCNN is trained without random sampler on the long-tailed Elvis dataset. In such a way, the imbalance between positives and negatives gradually increases with a range between 1/7 to around 1/10,000. Arrest loss can successfully train all these configurations without any tuning. On COCO dataset, it performs the best when more data is available after the random samplers are removed. On the other hand, when the samplers are removed, the performance of the standard cross entropy and GIO loss combination rapidly degrades. In this tutorial, we first discussed the basic ways of evaluating visual detectors, then presented an analysis of performance measures and explained why LRP error has advantages over the existing ones. And finally, in this part, we aim to delve into how the gap between the training and evaluation can be reduced by introducing identity update and its applications to optimize average precision loss and LRP-based loss functions. We sincerely thank all the institutions that contribute to this tutorial. Thanks for your time.